In this video, we're going to cover an application of the convergence of power series and infinite series by looking at a specific type of series called a Taylor polynomial or Taylor series, or Maclaurin polynomial, Maclaurin series. These are each of these are ways to approximate functions that are not necessarily easy to write a rule for, but we can approximate them using polynomials and using the specific process that that Taylor and Maclaurin each came up with. As a starting point, we're going to analyze this function e to the x. And we'd like to come up with a polynomial that approximates what e to the x is. So a polynomial that has the same sorts of, when I say approximation, I want this polynomial to have the same properties of e to the x. Namely, we want a polynomial with the same derivatives. So if a polynomial has the same properties as this function, then they should be very similar to each other, and they should give better and better approximations the closer each derivative is. So to do that, we'll start with some look at some various more refined approximations as we go. So maybe we'll start with, call this the zeroth order approximations, and we'll approximate this near x equals 0. Near x equals 0. My handwriting is especially bad today. Near x equals 0. Okay, so that would, I think, a polynomial with whose approximates this near x equals 0 is just, well, the polynomial we get if we just plug in 0 for x. And that would be e to 0, which is just 1. And I think we can agree that the graph of e to the x in the line, horizontal line y equals 1, while they're close to each other right at x equals 0, they quickly diverge. And I've got a picture or a graph of this on Desmos that I can pull up. So note that the graph of the horizontal line y equals 1 and the graph of e to the x are close to each other, near 0, but they quickly are not even close to each other. We can do better. Let's get a first order approximation. Meaning we'll have the value of the function at 0 be the same as our original, and also the value of the first derivative of our polynomial to be the same. So I'm thinking we'll build a polynomial that looks something like this. In order to get a first derivative at 0, we'll want some polynomial that's our 0th order plus some coefficient times x. We want the derivative of this polynomial to be the same as the derivative of our original function. So I think we want the derivative of our polynomial, which happens to be 0 plus a. And this should be equal to e to the derivative of the original polynomial. Since we've chosen this very nice function, the derivative of e to the x just continues to be e to the x every time. So putting this together, I think our first order approximation for this function e to the x as a polynomial will be 1 plus 1 times x. And we can see that they are, and I'll pull the graph up. And now instead of the horizontal line y equals 1, here's the graph of line 1 plus x, which, well, what do you know? It's, again, the same at x equals 0, but it's actually kind of hugs the graph much, much better than the horizontal line. It's kind of similar to the graph of y equals e to the x for a little bit further along than the original horizontal line, but it, again, quickly diverges. Okay, let's refine our estimation. Let's get a second order. this should be a function whose a polynomial whose second derivative, whose original value, whose first derivative, and whose second derivative is the same as our original function. If I differentiate this a few times, first derivative cancels out makes the 1 equal to 0, makes this x equal to 1, and this equal to 2b times x. The second derivative will be 0, 0, and 2b. So the second derivative of our approximation here, note, is just 2b. And again, this should equal to, the second derivative we want to be equal to the second derivative of the function at 0. So again, the second derivative of e to the x is still e to the x, and e to the 0 is 1. So this tells me that I want b to be 1/2. So a second order approximation of e to the x should be 1 plus x plus now 1/2 times x squared. And in keeping with our graphs, note that this was our first order approximation. Our second order approximation, well, it now is very close to my graph, a little bit further away than the line. It still diverges pretty quickly, but it's now closer to the graph for longer of e to the x. Do this one more time, and then we'll wrap this discussion up here. How about you look at a third order? This would be a polynomial whose first three derivatives are all the same. So I think I should start with 1 plus x plus 1/2 x squared. And now I want an x cubed term. Note that I want the third derivatives to all be the same. To be the same as the original function's third derivative at 0. Note that by the time I get to the third derivative, each of the first three terms is going to eliminate itself out to be, it's going to work its way down to 0. This third term, however, does something interesting. The first time I take a derivative, I get a 3 times c squared, and this exponent drops to a 2. The next derivative I take, I'm going to bring the 2 down, so I'm going to have 3 times 2, and then x to the 1. The third derivative, or the second derivative I take is going to bring the 1 down, and I'm going to be left, bringing the 1 down, and I'll be left with the third derivative, bring the 1 down and make this an x to the 0. So by the time I get to the third derivative, this is 3 times 2 times 1 times c, which is 6. Or maybe the pattern I'm trying to get you to notice is 3 times 2 times 1 is 3 factorial. So it looks like, and again, this should be equal to the third derivative of my function at 0. I plug in 0 again, this should be equal to 1. This tells me that c is equal to 1/6, or 1, maybe I'll write it in factorial notation, 1/3 factorial. So my third degree approximation could be 1 plus x plus 1/2 x squared plus 1/3 factorial x to the third. And as before, if we look at the graph of that third degree polynomial, note 3 factorial is 6. Now here's a cubic that again is now an even better approximation of my original function. Again, it diverges away from it pretty quickly, but it is now hugging the graph now even longer than the previous one. If you continue this pattern, you can find a fourth degree approximation. The d term ends up being unsurprisingly 4 factorial. And now here's a fourth degree polynomial that now is hugging the graph for quite a while. And generalizing, I've made a slider here to look at each of these approximations kind of in an animated way. And as you go, the further along The higher order approximation, the better and better my approximation gets for longer and longer. Note that you can't even tell the difference between the polynomial and the exponential in this region of the graph. And the further along I go, the longer this tail stays next to the graph. Oh, too, is my slider goes up to 15. So putting that together, we'll state what a Taylor, the rules to make a Taylor polynomial. And then in the next video, we'll look at some examples of using this. A Taylor and or Maclaurin polynomial of degree n is written in the following way. We say a function can be approximated by a Taylor polynomial we say centered at x equals c, at x equals c, in the following way. We say the Taylor polynomial of degree n that approximates this function is using this exact recipe that we came up with up here. Namely, it will have the value of the function at the center plus the derivative of the value at that center divided by 1 factorial times x minus the center to the first power plus the second derivative at the center over 2 factorial times x minus c to the second power. You continue on until you get to the nth derivative for the nth order over n factorial, again at the center, times x minus c to the n. This is the same process we used to come up with the polynomial in the example above. We note that we say that if the center is 0, these are called Maclaurin polynomials. So Taylor's the more general form. Specifically, if the center of your polynomial is 0, we call them, they're named after Colin Maclaurin, or a Maclaurin polynomial. So there's no difference in the creation of them. Just if we state it's a Maclaurin polynomial, that specifically means that this c term is exactly 0.